Okay, so we've just gotten into connected objects, and the assumption behind connected objects is that the net force, so I'm trying to write with a laser pointer there, net force on the system equals the mass of the system times the acceleration of the system. All right, that's our assumption. Okay, we're taking the whole system, and these two objects, even though they're separate objects, this mass 1 and mass 2, which by the way are not labeled, are they? I'll have to label them. I'll put a mass 1 right there, and I'll write in yellow in the other one, call it mass 2. Mass 2, they're separate objects, but they're connected by this wire or by this cable. All right, now again, you're probably going to need to reiterate the fact that the cable is assumed to be massless. We know in real life it's not. It does have some mass, but we're ignoring it for now. And this whole setup right here is called an Atwood machine. And an Atwood machine is a machine that's going to turn one way or another because of a difference in weight force. All right, now both of these masses, since they're connected by a cable that is looped over a pulley, that's what this is right here, a pulley. That means even though both of these masses are acting downwards, they're acting against each other, right? Because what does a pulley do? A pulley changes the direction of a force. All right, so you've got tension created by mass 2 pulling down right here, and you've got tension of mass 1 pulling down right here. And so these two weights, even though they're being both pulled vertically, are acting in opposition to each other. Now, look at these masses for a minute. We know that the masses is going to be M1 G right here and M2 G right here. They're going to be creating weight. And look at it. Which one is going to win, as it were? Well, this one right here, right? Because it's going to be it's 10 kilograms, and this is only 8 kilograms right here. We'll calculate it out, what they actually are in terms of newtons in just a second. But we're going to probably be able to predict that this system is going to rotate in the counterclockwise direction. Now, it's important to establish a direction because since we have two forces acting in opposite directions, one's going to be negative and one's going to be positive. The funny thing is that it doesn't matter which is positive and which is negative. You can call clockwise negative, you can call, counterclockwise negative, you can call clockwise negative. It really doesn't matter because if you call this direction negative, then you're going to get a negative acceleration. But it is important to establish one direction is negative and one's positive. So since we know that the machine is probably going to turn counterclockwise, why don't we just call this direction positive and that direction negative? Okay? If you got it wrong, if you picked it the wrong way, it really wouldn't matter. It just means that your answer would have that sign in front of it. But let's find the acceleration of the masses. Now we're also going to find the tension in the cable as well. The tension is this force that is acting in two directions there and also two directions there as well. It's an internal force. So it's not adding to the motion of the machine, but it is a force that is connecting the objects, very much like a contact force. But let's go ahead and just start by finding the acceleration of the masses. Okay? So we have our net force of the system. Let's make a statement about the net force in the system. Net force in the system is going to be, let's make a global statement first, all right? Mass of the system times the acceleration of the system, right? That means that all parts of the system, mass 2, which is going to be sliding up, and mass 1, which is going to be sliding down, are going to be accelerating at the same rate. But what's also true about the net force in the system is a component statement about the net forces. We have two forces acting against each other. We have force 1, or I should say M1G, the weight force 1, acting in the positive direction. All right? I'd like to color code that, but I'm afraid that the yellow is not going to show up very well. I'll make that orange, okay? Mass 1 times gravity. And mass 2, and I can draw this in purple because it should show up, is acting in the negative direction. Even though mass 1 and mass 2 both have a weight that acts downwards, since those forces are draped over a pulley, they're acting against each other. So this is going to be the negative direction. This is going to be the positive direction right here. That's why we've got a minus sign in front of mass 2g. Okay? So let's find out what the acceleration is. Let's set these two statements equal to each other because they're both statements for net force. So we can say the mass of the system times the acceleration of the system equals m1g minus m2g minus m, change of colors takes a little while here, so sorry for the delay there, m2g, okay, mass 2 times gravity. And so, of course, acceleration itself, acceleration of the system is going to be m1g minus m2g, m1g minus m2g, all divided by the mass of the system, m cis. Okay? Hope to be able to squeeze all that in. Mass 1 times gravity. In fact, let's make this a little bit easier on ourselves. Let's take this numerator here. Let's just factor out g. Let's put it out front, and then we'll have mass 1 minus mass 2. All right, so g, that way we'll save some space as well. G comes out front, and then it's going to be mass 1 minus mass 2. And I think in the attempt to actually save space, I just wasted one more line right here, but that's all right. Divided by mass of the system, that's mass 1 plus mass 2, right? You know what, M1G in red, I'm going to take and I'm going to delete you because you are in the way. That's going to go away right there. And see M1G, M2G. Let's just go ahead and put our values in. I'm just going to write all in black because otherwise it'll take forever to change all the colors. So 9.81, that's our G, right? Times mass 1, which is 10 kilograms, minus 8 kilograms. Sorry, I'm not color coding anymore. It just takes too long. All divided by mass 1 plus mass 2. So that's, we can do that in our heads, right? 18 kilograms. So what's really causing the system to move is the difference between this mass and this mass right here. So the difference is only going to be, we're going to see it's 2 kilograms, right? Only 2 kilograms worth of mass times gravity is the force, the weight force that's causing the system to move. And that force is trying to accelerate the entire system, the entire 18 kilogram system. So the weights are acting against each other, but the system is still the same mass. The total mass, 18 kilograms. So what do we get? I can do 10 minus 8 in my head. So take that times 9.81 divided by 18. That's going to be 1.09 meters per second squared. Right, that's our acceleration of the system, which isn't very fast. But if you think about it, most of the weight force of this block and this block right here are simply acting against each other. They're causing the tension in the string to be pretty tight because they're both pulling away from each other, creating a lot of tension. But the whole system itself barely has any net force on it because it's only 2 kilograms more on this side than on that side. So let's now find the tension in the cable. All right, so I'm going to do this on the right-hand side. I think I'll be able to have enough space for T. What we can do now is we can look at each one, or either one of the two masses right here and find out the tension that is causing that mass to move. Because this mass is going to be moving upwards, right? Why is it moving upwards? Because the tension in the cable is pulling it upwards. Despite the fact that you've got the mass 2's weight pulling right down, the tension is pulling it up, and it's giving that mass that acceleration that the whole system, by the way, has. All right? So let's look at mass 2. All right? We could look at either one, quite frankly. But for mass 2, right there, what do we have going on? Well, we have the downward weight force, M2G, right? And we're calling it the negative direction. But we also have the upward force. What's causing it to move upwards? Well, tension is causing it to move upwards because if that rope were cut, mass 2 would fall straight down, right? So tension is pulling up, and we can pretty safely assume that the tension in the string, which, by the way, is a tension all the way over here, right? It's a tension all same throughout. The tension in the string is going to have to be greater than the mass 2 times gravity because the tension is winning out. It's causing mass 2 to rise up. All right, so our first statement about net force for mass 2, let's write this in purple. And I'm going to stop changing colors right here. Net force on box 2 is going to be T in the positive direction minus M2G, right? What's also true is that the net force on 2 is going to be mass of 2 times the acceleration of 2. And we know that the acceleration of box 2 is going to be the acceleration of the entire system, which we just found down here. So we can plug in the acceleration of the system in for box 2. Let's set these two equal to each other and solve for t. All right? So t minus m2g equals m2 times acceleration, 2. So therefore, tension in the string is going to be m2g plus mass 2 times acceleration of 2. And again, the acceleration of box 2 is the acceleration of the whole system. Let's factor out, again, I'm factoring this out about losing space. Let's factor out the m2 equals m2, right? Because that can come out front. So g plus the acceleration of 2, which is the acceleration of the system. And so now we know all of our values. We can just simply plug them in. What's the mass of 2? That's 8 kilograms, right? I'm just going to put 8 because I'm running out of space. G is 9.81. And acceleration of box 2 is the acceleration of the system. That's 1.09 plus 1.09 meters per second squared. Let's solve for our tension in the string. And that tension is going to be the exact same tension that connects to box 1 as well. We just chose to solve for tension using box 2. 9.81 plus 1.09. That's good. It's going to sound like, okay, 10.9 times 8. 87.2 newtons. 87.2 newtons is a tension in our string that is going all the way over the pulley, over to connect box 1 and box 2. And we set that by looking, but we found that by looking just at box 2. We made a net force statement for just box 2. And we were able to know the acceleration of box 2 because the acceleration of box 2 is going to be the same as the acceleration of the entire system, which is what we found first. All right, so that's your first Atwood machine problem. Took up a good deal of space right there, but hopefully it makes some sense to you and there's a certain logic behind it. So please let me know if you have any questions. I'll be glad to go through them with you. But for now, thanks for following along, and I'll see you on the next one.